In this video, we're going to talk about centrifugal pumps. We will describe how they work, list the different types, show how to compare energy at inlet and energy at outlet using Bernoulli's equation, show how the energy of a pump is added to a system using Bernoulli's equation, and show some real-life applications.
A centrifugal pump is one of the simplest pieces of equipment. Its purpose is to convert energy of an electric motor or engine into velocity or kinetic energy, and then into pressure of a fluid that is being pumped. This conversion of energy occurs in two main parts, the impeller and the volute. The impeller is the rotating part that converts driver energy into kinetic energy. The volute is the stationary part that converts the kinetic energy back into pressure. Liquid will enter the pump suction at the eye of the impeller. When the impeller rotates, it spins the liquid setting in the cavities between the vanes and outward and imparts centrifugal acceleration. As the liquid leaves the eye, the impeller creates a low pressure area and more liquid is allowed to enter the pump inlet. The impeller produces liquid velocity and the volute forces the liquid to discharge from the pump, converting velocity to pressure. This is accomplished by offsetting the impeller in the volute and by maintaining a close clearance between the impeller and the volute at the cutwater. The cutwater, shown here, is where the water will enter and exit. Please note the impeller rotation. A centrifugal pump impeller slings the liquid out of the volute. It does not cup the liquid. This process of inducting new water into the eye of the impeller is called priming. Priming occurs when the eye of the impeller is creating a low pressure zone by air pressure spinning and rotating along with the water. This is important because new water cannot be induced otherwise.
Okay, so in this section we're going to be talking about three different types of pumps. Now there's a lot of different components to a lot of different types of pumps, such as, if they're self-priming, non-self-priming, things like that. But for the purposes of this video, I'll kind of do a basic overview of these three, which are single stage, two-stage, multi-stage. Single stage is what I showed before. It has a single impeller, a single water cut, and it goes in. The impeller increases the pressure on the inside increases the discharge pressure. The single centrifugal pumps are used for large volumes of liquid, water, whatever it might be, and it might not create a high enough pressure for large projects, but it is good and cost effective for small end things, maybe such as an air conditioning, something like that. If you need more pressure than that, that's where the two-stage will come into play. And essentially this is just two single stages linked together in a series. After going through the first chamber and impeller, it will be discharged into the second chamber, where then the pressure will be increased again via the same process. So basically the ending discharge pressure will be higher than single stage. Now, if you are looking at more commercial applications, such as maybe an oil refinery, even if you go to a ski or snowboard place, how they create the fake snow, that's where you would need a multi-stage centrifugal pump. Now, multi-stage centrifugal pumps have multiple liquid chambers that are connected in series as well. Fluid enters through the first chamber, goes into the second, goes into the third, and however many stages that has, it will repeat that process that many times. So basically, the more stages the pump has, the higher the final discharge pressure. These pumps have a unique ability to produce higher and higher pressures with the addition of every stage, but the flow range always remains constant for a given RPM. So essentially that means that it's a very efficient machine, even though it might be cost-effective or not cost-effective up front, as they can be pretty expensive. In the long run, it will save money depending on how big your project is or job is, whatever the workload might be. There are actually two types of multi-stage centrifugal pumps. One is a horizontal and one is a vertical. With the horizontal, I will show here, this type of pump is segmented with casing, and it has multiple interstage components. The rotating assembly is held between bearing housings, making the assembly more balanced for high pressures. Basically, the layout of how this is, it will be able to handle higher pressures than a vertical. Like I said, typically they handle higher flow rates as well due to this increased pressure, and The horizontal configuration of a multi-stage pump is best applied in applications such as boiler room showers, pressure boosting, like I said, snowmaking, mine dewatering, things like that. So they are pretty maintenance intensive, however. You have to be pretty specially trained, and they take a high skill set to work on these. But even though they are costly upfront and costly to have somebody trained to work on these, they are very cost effective in the long run. Now, vertical multi-stage pumps, they are stacked. The stages of the shaft are stacked on top of each other. So basically, they can fit into better spaces. You don't have to allocate as much room for these. Like I said, clearance is small, so clean water applications are probably the best for this pump, such as high pressure shower systems or maybe pressure washing, boiler rooms, superheaters, things like that. Vertical multi-stage pumps are great for areas that don't have much footprint to spare. Its ability to deliver high pressure output with a single pump body and motor combo, that is also a plus.
Here we have a Bernoulli equation example. This equation you see here shows the energy between any two pumps. Our goals are to compare the energy at inlet and the energy at outlet and show how the energy of a pump is added to a system using our system right here with the two open water systems, a pipe with two bends, and a pump right in the middle. Okay, so we need to start by splitting up the equation and thinking about what we know first, right? So what I did first was I created a datum. I did the center of the lower pipe to the center of the higher one. The distance was 10, so Z1 equals 0 and Z2 equals 10. Because it is an open system, right, where the water is open on both sides of the pump and of the pipe, velocity is going to equal 0. So V1 and V2 equal each other. And because both are over 2G, they cancel each other out because they're on different sides of the equation. Next, we're going to look at the pressure, okay? The pressure in this system is the pressure of the atmosphere because it's an open system, okay? So the pressure would be 14.7 psi on both sides. And then pressure is divided by the specific gravity of water. And since both of these are equal to each other, we can also cross that out in the equation. So after eliminating all those, it makes the equation really easy, right? It's 10 equals 0 plus the energy loss due to the pump and the energy loss due to friction. This makes the equation relatively easy. You have the energy loss to the pump that will either be given to you, or that is what you'll be solving for, or you'll have the energy loss due to friction. If you don't have either, you'll have to solve for the energy loss due to friction using the friction factor, local loss coefficient, and the equivalent length of a pipe.
There are several different applications you can talk about when talking about centrifugal pumps. However, I would like to talk about the commercial and industrial sides. There are some residential sides, but they're not very common. The first I would like to talk about would be pressure boosting. This is used more commonly in like a water supply for a building. It's as simple as increasing the pressure from one location and using that to transport to another location. Another one I would like to talk about would be wastewater applications. It's most commonly used in raw wastewater pumping. It could also be used in lift stations, recirculating flows, return activated sludge. And the last one I would like to talk about would be heating and cooling distributions. This is most commonly used in HVAC systems. It supports the operations of chillers and boilers in a system. And again, almost all of these are commercial or industrial size. There are some smaller residential size, but they're not very common.